Hello everyone, January 24th. Alright, yesterday was a total fiasco. This problem really bad. So this morning, took it to another ride and I was able to simplify the implementation and get a little bit better. But still, I did not see that this is a graph problem. I thought this is purely a simple DFS. Oh, not DFS, the DP. I thought this is a DP problem. And this apparently is not a DP problem. If you think about it, it is indeed a DFS. You try to reach the end as fast as you can. But I couldn't figure out why DP doesn't work. I mean, there are a lot of things to consider in the DP for sure, and it's definitely not the fastest. So what I found is, if you look at my earlier attempt, right, this solution, when I do the queue, right, I have to put basically four states in it. And the visited, I also split into two states, whether it's a jump or not a jump. And then just take ridiculously long. And in the reversed one, there are two differences. The main difference. The first is we are no longer doing coordinates anymore because it doesn't really matter the coordinates. We spend a lot of time in this trying to figure out, okay, where do I go first? Not this one, right? Not this one, but the other one. The previous kind of solution, we try to figure out, okay, when you walk 6 steps to the right and then you have to walk 6 steps to the left, right? All this very complicated. So in this solution, everything is based on label. You just add 6, right? You just add 6 to the label and then trying to check. And then I do have to build kind of a reverse, so I know what board value is corresponding to each label, and then I know like if a certain label represents a jump. So that's the first big difference, which significantly makes things easier. Like in here, the queue, I only put label one of them in it. The second is about the visited. I just realized that you don't have to consider two different states when you reach, let's say, a jump, because if you do the jump right here, now this is where I do the jump, right? I will do the jump right here. So every time when you do a jump, it goes into the next layer in the BFS. So when it comes out, it always just do regular walk, right? So it doesn't really matter. You don't really have to consider like a double jump. Would that happen? No, it won't happen because the first jump guarantees that the next one is not going to be a jump no matter what. So that means the visited can be as simple as just whether it has been seen before, right? And that's basically it. That's basically all that is needed to deal with, right? And no matter how you reach a cell, when you reach a cell, it's been visited and you should not visit again. So that's where here, right, the next label should not be visited, or the jump should not be visited. And everything else is just simple and easy. I don't know why, it just troubled me so much. And this is just BFS, right? It's just BFS. I don't know what's the implementation here. But from what I can see, it's the same. You see the queue, I use a deck, it doesn't really matter. And then that's the distance. That doesn't really matter either. But they're recording the distance. But I'm just returning the distance the first time we hit it. They do row and column though. This one, they build the label so they know the row and column. And then destination is going to be, if this is not equal to, there will be this. Otherwise, it'll be next. If the next one is this, destination equals, this is the step, distance plus 1, and I'll put a destination into it. And this is where they handles, right? If the next one is not, then they don't put it. I don't know if this is right. Hold up, this is weird. That's an interesting implementation. So the next will just be all of those, right? And then we'll do the next. We know the row and column, so we get a board. If the destination is a jump. Oh, this is distance. It doesn't really matter. It's a distance. It's a distance. So this means has not visited, right? So you have not visited. We do the visit. We push this in. Yeah, it doesn't really matter. And will be the current plus 1. Well, what if it's a jump? Don't know, but don't care. I like how I think about this, so I'll just keep it that way. Yeah, but still very disheartening that, I mean, my performance has been dropped for quite a few days. So let's see if we can bring it back. All right, find the closest node to given two nodes. You're given a directed graph of n nodes, number from 0 to n minus 1, where each node has a most one outgoing edges. Each node has a most one outgoing edges. The graph is represented with a zero indexed array edges of size n, indicating that there is a directed edge from node I to node edges I. Okay, so from 0 to 2, 1 to 2, 2 to 3, and 3 has no outgoing edge. If there's node, it's not minus 1. You're given two integers, node 1, node 2. Return the index of the node that can be reached from both these two nodes, such that the maximum between the distance from node 1 to that node and node 2 to that node is minimized. The maximum between the distance, so we find a node, and that node has a distance to node 1 and distance to node 2, and the difference of that, we want to find the maximum difference of that, and we want that maximum difference to be minimized. There are multiple answers, return the node with the smallest index, and if no possible answer, return minus 1. Edges may contain cycles. Okay, so node 0 and node 2. No, node 1 is 0, so we have 0 and 1. Okay, 0 and 1. We want to find the node, the distance. We'll go from this towards that node. Go from this towards that node. One here is only 1, so distance is 0. We can also choose this. Distance is 2, 2, and also 0, so distance is the same. The difference is the same. Hold on. The distance from 0 to 2 is 1, and the distance from 1 to 2 is 1. The maximum of those two distances is, how is it 1? Huh? How is it 1? Hold on, let me read it again. The maximum between the distance from node 1 to that node and from node 2 to that node is minimized. The distance from node 0 to 2 is 1. Yes, that's 1 distance. And the distance from node 1 to node is 1. The maximum of those two distances. How is it 1? How is it 1? The maximum of these two distances. The one distance is 1. The other distance is also 1. The difference should be 0. This is a weird. Okay, let's try this. 0 and 2. The maximum distance I can go to 2 itself. The distance from 0 to 2 is 2. The distance from 2 to 2 is 0. The maximum of those two distances is 2. Cannot get a node with a smaller maximum distance than 2. So if it's a 0, well, if it's a 0, if I go 1, then from 0 to 1 is 1. From 2 to 1 is impossible. So that's impossible. If it is 0, from 2 to 0 is impossible. So that's impossible. Nah, I'm still hanging on this one. This does not make any sense. This should be 0. I mean, maybe we can change, but it only has 1 outgoing. Yeah, I don't think this is 1. The maximum of the 2 distance, this should be 0. I mean, it does make sense because 3 is also 0. Ah, maybe what we can do is use this, but we can change this. So instead of, we put 3 here. So 1 to 3, 0 to 3, 1 to 3, 2 to -1, and 3 to 2. Basically, I swap these two, right? So I expect the result still be 2 because that's the difference is still 0. So if it's still 2, then I think our understanding is correct. Expected 3, that is interesting. That is very interesting. Then I don't know why it's 3, right? We have 0, 0 come down to 3, 1 come down to 3, 2 come down to nothing, and then 0, 1, 2, 3 come down to 2. Return the index of the node. Index of the node that can be reached from both node 1. Node 1 is here, node 2 is here. That can be reached such that the maximum oh, it's not the difference. It's the maximum between the two distances. The maximum between the two distances. The maximum between the two distances is minimized. Ah, I thought it's a difference. No, it's not. Okay, so the maximum difference from node 0 to everything. So we're given node 3. The maximum difference is 1. We're given a node that is 2. The maximum difference is going to be 2, right? So we want this maximum distance to be minimized. So when the 3 is going to be minimized, so we pick 3. Okay, that makes more sense now. That makes more sense. So basically, we're given 2 nodes, right? And we have all the rest of the nodes. And we need to know if they can reach, what's the maximum distance to reach. I mean, each node can only go out once, but it can be a circle. So maybe let me see what the circle can do. How about 0 to 1 and then 1 to 0? So the right out will be 1, 0. If it's in this case, we probably need 3 in order to have 2, because now it's fine, we can do 2. So if I pick 1, maximum distance is going to be 1. If I pick 0, so that answer should be 0, which means if I do 0, 1, no, 1, 0, and 1, 0, answer shall be 0. We shall pick 0 because that the distance is 1. Expect 0, that is correct. But to reach a node, so what's the maximum distance, right? That's the question we want to ask. I mean, of course, we have some -1, so those cannot go out. Now, which means if the given node is -1, then it could only be itself. Yeah, here, 2 is, then we can go by itself. That's the only possibility, right? So if any one of these is -1, that's the only possibility. So yeah, that significantly reduces the complexity. And if we actually try this example, if I have hold on, just playing with this. If I have 0 also pointing to itself, and I need to go 0 and 2, that should be -1 because they can never reach another one. So if both are -1, it should be -1. Yes. Okay, so now we need to figure out how to find the maximum distance to reach. I mean, we can't, because it'd be the maximum. So we have the two starting nodes, okay? We have node 1 and node 2. We have two starting nodes, so we don't know where they are. And then they have the node leading away from them, right? And then that node, we have something leading away, and then we have something leading away. And since each one leads away only once, okay, so we can basically traverse the entire thing until we reach a point. Either we form a circle, right? It will form a cycle. So like we lead from one, and then we go out and out and out and out and out and out, and eventually, boom, we hit back at one of the things. And then it's a cycle. Then there's nowhere else to go. Or we just keep going until we hit one that, yeah, because everyone you can only get out once. You can only get out once. You can only get out once. And at a certain point, you either end up with a node that doesn't have any out degree, doesn't go out, or you end a node that has been visited before. And if you go to that node visited before, then that's a cycle, right? So you can go through this entire thing, take the record of the distance, and the thing is, there shall only be one path to any other node. There shouldn't be another path to another node. Because if there is another path starting from one node to another, that indicates along the way someone, hold on, let me think. Along the way, like if I want to have one path going to this node, is it possible to go from this to another path while everyone only has one out degree? Well, if I want to hit this, right, I mean, we can have one node hitting like with two in degree. That's possible. I mean, someone has to be out degree. Someone has to be an out degree. And for these two to do, then there must be one node that has two out degrees. Otherwise, it's not possible. Therefore, we just traverse from node 1 to everything. We will record. Now, here is the thing. Here is the thing. Here is the thing. Do we count the first time they do, or we count the second time they do? I think it should be the first time they meet. Because if it's not, I can say in this case, I think in the 0, 1 case, I can go 0 to 1, 1 to 0, 0 to 1. I can say from 0 to 1, it takes like infinite step, right? So that's not going to be right. So it should be the first time you hit, right? We can actually try this. Let's say 0 to 1, 1 to 2, 2 to 3. 3 comes back to 1, okay? So if that's the case, from 0 to 1 should be one step. Or do we do 1, 2, 3, 4, 4 step to 1? How can we test this? Well, we can choose 0 and 1, 0 and 2. Because from 2, the furthest you can reach is 1, right? From 2, the furthest you can reach is 1, which will take 1, 2, 2 step. And from 0, if we want to go 1, it's either 1 step or 1, 2, 3, 4, 4 step. So the maximum shall be 4, right? The 1. And if we go with 2, then that's 0, that will be 2, right? The minimum. We want to find a node such that the maximum between the distance and this will be minimized. So we want to find the node that'll be minimized, which in another case, if we do have cycles, we only want to cycle do once because we take the maximum and we want to minimize it. So we want the maximum to be small. So yes, this is the first time we hit. So basically, yeah, for each node, we'll record on the number of the length, right? The length. So for node 1, we're gonna get an array. We have all the length. For node 2, we have an array. We have all the length. And then what we need is to compare the two, right? For each one, we compute a maximum between the two. So we will form yet another array with the maximum of the two. And if it's not possible, we can just max out infinity. And we will hit, when we're done, we'll sort and then return the index of the smallest maximum distance. Okay, let's give this a shot. And hopefully we have better performance today. All right, take this for a ride. So we have dist1. Okay, I can say 0 times when n. Okay, 0 times n. And dist2 will be 0 times n. Okay, so we're gonna take dist node 1 for a ride. What do? We say, maybe we can do this. We define a function. Yeah, we define a function, def dfs, okay? And then we'll say the current node, right? And we don't have to return anything, right? We'll return nothing. And we need a visited, okay? So what we'll do visited. Yeah, we can pass visited in here. Visited. Okay, this is gonna be a set of integer. Okay. So now what we're gonna do is, from the node, we need to know the next. Oh, we also need dist. Okay, dist can be integer. Okay. So when it start, right? When it starts, say dfs. I know we start from node 1, right? With a set, a visited, and the distance is 0. So the first thing we say visited.add node, right? So this node is visited, and then we're gonna find its next. So we're gonna say next shall equal to edges node. Okay. What it should do is also add visited and a dist. Oh my god, we need to do the dist as well. Holy crap. How do we do the dist? Dist list. Right, list of integers. And then we say dist list at the current node shall equal to the distance, right? The distance to here. Once we're done, we find the next, and then we say if next is equal to, the next is equal to -1, or next is invisited, then we'll return. That's the end. Otherwise, we're gonna dfs next node visited, we pass this, and dist +1, and then we pass dist list. So we keep going until we finish. So we'll do this and then dist1, and we do dfs node 2 with a set 0 and dist2. So when we're done, we have dist1 and dist2. Now we need to, we can say for I d1 d2, okay, I d1 d2 enumerate zip dist1 and dist2. Actually, these has to be math.inf if the things that I'm thinking shall work. Okay, and then we're gonna do maximum, right? Because they go to we want to max between the two, so d1 d2 maximum, and then I is the index, right? And then we want to find the maximum, no, the minimum of this. What would you return if I do minimum? That's an interesting question. I actually don't know. Let's see. If I have a equals 1 2 0 4 and 2 3, okay, what max a will return? Will return 2 3, and minimum a shall return 0 4. So yeah, we want a minimum. Oh, they might, but maybe the minimum, let's say if we have 0 4 0 3 and a 0 2, how about that? Let's see what the minimum returns. Minimum a returns 0 2, so choose the first one and choose the second one because we want the smallest index. So that's fine. So what we need to do is do the minimum of the whole thing, okay? Minimum of the whole thing, and then we can do the result, which should be the minimum of the whole thing, and 1. Nah, we should do d and index equals minimum of this, okay? And then we say if d is smaller than math.inf, then we shall return index. Otherwise, we shall return -1. Okay, so this is my solution. Let's take a look. So we have a few test cases for those to work. So the 2 test cases that's provided, and I think I also have a few that I just made myself. So like this one, -1, 2, -1. If we do 0 and 2, shall return -1. That's 1. And I remember we also have this 1 0, and 1 0 shall return 0. Okay. All right. Let's see if we got any luck today. Node 2. Closest edges, node 1, node 2. Okay, so these are correct. Let me double check here. We take on all the test cases. Okay, give this a shot. Let's see how we go. Boom. Okay, we redeemed a little bit from a little bit bad performance from the previous few days. And not the fastest. I only 27, but at least it works. Okay, at least it works. 2359. Right. The fact that each node has at most one outgoing edge, right, means that any node can only be reached by node 1 or node 2 in a unique path, or not reached at all. Therefore, we can start from node 1, right? Traverse the entire path to obtain the unique distance from it to all the nodes accessible, right, to it. We do the same to node 2. Any nodes not accessible have the distance set to inf. Then we just compare the distances to each node, the two distances to each node from node 1 and node 2. Right, node 1 and node 2 get their max and find the overall minimum along with the index, along with the node that allows such minimum. ON and performance, nothing special. We have a solution, can take a look. We can do breadth first search. Oh, is that this week's item, breadth first search? The breadth first search will always, so we get the minimum distance. Yes, we get the minimum distance, and we get the minimum distance. I think the overall shall be the same. So the breadth first search. We do BFS, and then what do we get? We have a vector which gives the minimum distances, and then we go through, yeah, that's the same, DFS. Can only be one path, exactly. Yes. Yeah, DFS recursive. Recursive is I mean, both works. Okay, so yeah, I'm not writing BFS. This is enough. Okay, so now we have a little bit bandwidth. I think I will take a look at this. Probably not do it, just think about it. So what does this one say? You're given a zero index integer array, stations of length n, where stations I represents the number of power stations in the ith city. So we have all the cities. Look at the title, maximize the minimum power city. Number of power stations in ith city, okay. Each power station can provide power to every city in a fixed range. In other words, if the range is denoted by R, then the power station at city I can provide power to all city J such that I minus J. What's I again? I is a city. What's J again? Oh, other cities is also index. So if it's smaller or equal to R, and they're okay, note that X denote absolute value, that's fine. The power of a city is the total number of power stations it is being provided power from. The government has sanctioned building K more power stations, each of which can be built in any city and has the same range as the pre-existing ones. K more power stations. Given the two integers R and K, return the maximum possible minimum power of a city if the additional power stations are built up. What does built optimally mean? Built optimally. In other words, if the range can provide power to every city, maximum possible minimum power of a city. Hold on. The maximum possible, right? So we want to find the minimum power. So there are many minimum power of a city. The maximum possible minimum power of a city if the additional power station built optimally. Note that you can build a K power stations in multiple cities. One of the optimal way is to install both the power station city 1. So 0 is provided by 4, 5. 1 is provided by 9. 2 is provided 13. It's provided 5. So the minimum so by building the power stations, each city can receive, we can get a power. And what we want to find is the minimum of the power that they can receive. And we want to get a maximum of this minimum power. Which means without building, what we have, city 1 has 3. City 2 has 7. City 3 has, what's that, 11. City 4 has 9, and City 5 has 5. So before building, City 1 has only 3. So before building, it should be 3. Right, which means, yeah, we actually do this. Let's say we will build 0 power station. Then it's basically just a computing of the original, and that's 3. Yes, I know what it means. Oh yeah, it's only 0, so it doesn't affect, so it's just by itself. Okay, so we want to find out the maximum. So basically, we have this setup without building power stations. Now we need to build power stations. We have K power station to build. And then we can build an anywhere, right? And then if we build anywhere, it can increase the power of this city and its surrounding cities. Okay? So we want to raise the minimum of them, which means if we build all on this, that's one of the optimal way, right? One of the optimal way. Now, well, we can say we'll have the minimum. Yeah, we can give the initial value, which is easy to do, right? We'll give the initial value. Basically, it's just it's a prefix sum, right? We can do a prefix sum and then just a sliding window thing. Now we can compute all of them very easily. I mean, we can just do a prefix sum, basically. Yeah, I'm gonna move. And then we move. Yeah, it's a prefix. It's not a prefix sum actually. So we have all this, and then we have all different ways to put the K. And K is 10 to the 9th. Okay. So if all of these we can put into different things, and now we put into that thing, at any, we basically raise with +1 on all the surroundings, right? With +1 on all the surroundings. And to make the smallest, we want to raise the lowest, right? So if it's already high, there's no point keep raising it, because we want to find the maximum possible minimum power, right? So now current minimum power is 3. So we need to find a way to raise 3. So to raise 3, what we can do is to raise 3 by itself, and then we will affect everybody else. But you can also put it in a more strategic place. What do you mean by more strategic place? The place where it's the furthest away. Because if you want to impact on others, interesting. The final impact. Or maybe we can say, because it's a range, right? If there are small city with small power within the range, then the ideal way is to build a power plant in this range. And I think maybe each step can be optimally computed. I mean, we built 2, right? And each one will add 3 power in total. So there will be 6 power in total can be added in this scenario. But no matter what, right? No matter what, the maximum a city can receive the power, the maximum is going to be 2, right? The maximum is going to be 2. So in this example, right? In this example 1, because the second smallest is 5, right? It's 2 larger than the smallest, which is 3. So in that case, no matter what, the maximum minimum is going to be 5. It cannot be more than 5, because each new power station can only increase your power by 1. So the question now is, if we have, right? So yeah, we can, think about, because you can always put everything in the smallest and then you raise. But if you think about a k, if k is huge, okay? If k is huge and we're able to raise everybody, right? We're able to raise everybody up, but we always want to focus on raising the smallest up. So we can say, okay, if you think about like a more greedy, we want a small to reach, right, to the others, and then we want both to go up to reach the others, and then we want all of them to go up, right? Then what does this mean? You know what? It feels like, what can we do like binary search type of thing? Because we're asking the maximum possible minimum power, right? And given the current, we do have upper bound. The upper bound is k, throwing all into the highest. That's going to be the upper bound. And the lower bound is going to be the lowest current that we have, right? That's the higher bound. That's actually not the high, and that can be the higher bound, because we just want to ask if it's possible. So now the question is, if given a minimum power, right? Because it's binary search, we have a middle. Given this middle value, can we reach it? Is it possible to figure out a scheme that we can reach this minimum value? We can try actually in this. So we're starting with 3, 7, 11, 9, 5. That's what we start with, right? And then we can say the total we can give is 2, okay, to a city. So the maximum is going to be 13. The minimum we can give, if we just give this and then we leave other thing not attended, so the smallest is 3. So we have 3 to 13, okay? So the first possible is 3 plus 13 is 16, divided by 2 is 8. So we say, is 8 possible to reach? Well, then we say, if we want to reach 8, okay, which is the smallest, so how many are smaller than 8? Well, we have 3, 7, and 5. They're all smaller than 8. And 3 requires 5, 7 requires 1, 5 requires 3. So added together, we require 9. At least 9 units is needed. But the total units can be given is 6, right? It's smaller, so 8 is not possible. So okay, now we say, because we want to find a maximum, right? Which means if we have the small, we want to go big. Yes, for small, we want to go big, which means, I mean, it's not possible. So we go down to 8. So now it's 3 to 8. Okay, now 3 to 8, that's 11, right? 11 divided by 2 is going to be 5. So we say, okay, is it possible to reach 5? Okay, to reach 5, we find only one of them that's smaller. And then we only need 2. And we can give 6. Now, there's also another thing that need to consider, right? Is when it's within the range. When it's within the range, you also need to think about the distribution if it's possible. But in this case, we only have 1. We have 1, and we require 2, right? We require 2. One of them required 2. So yeah, that's possible. So 5 is possible, okay? But we want to find the maximum, so we'll go at 1. So we'll go 6. So 6 to 8. 6 to 8 will give you 7. Is 7 possible? So we do it again. So 7, we find out that we have 3 and 5. That's smaller than 7. So they need to be brought up. So 3 requires 4. 5 requires 2, which means the total. Now 3 requires 4. That's not possible because each single one can only get at most 2. So this is not possible. 7 is not possible. If 7 is not possible, 8 will be brought down to 7. So now it's 6 and 7. 6 and 7 will give us 6. So is 6 possible? So for 6, 3 needs 3, 5 needs 1, 3 needs 3. That's not possible because we at most each one can get 2. So that's not possible. So 6 not possible. Now bring it down to 6. Now we get out. When we get out, right, because it's possible we go up, right, and then so we should return whatever get out minus 1. So it'll be 5. That is interesting, right? That's very interesting. What we can also do is, so basically what you're saying is there's a way to identify if it's possible or not by checking, right? By checking what's the need of the smallest. So we sort, right? We sort the array, and we know the smallest requires. If it requires more than k to reach the minimum, then it's not possible. We can just keep shrinking down. Now, there will be a situation where everyone is possible. Okay, everyone's possible. Then we can count the total, right? That's another way to check. If the total is required, total is too big, then that's not possible. Now, the final thing is each individual is possible, and the total is also possible. Now, that's interesting to deal with. Then we need to know the distribution. So all of them have a distribution, right? All of them have a distribution. Then if we lay them out, when they have their indexes, we lay them out, then we need to know if supplying one with whatever we need. Yeah, and it's possible to do because we can check the maximum overlay, right? So which means we want to deploy the new power plant with its left max reach with the leftmost city that needs it, right? And then we see how many they need. We deploy that and try to see on the right side. If it doesn't reach, if it reaches, then we can add, and then we can say, okay, how many does it need? And we do it again. And we do it again, and yeah, so every time we try to only on the leftmost reach, we try to reach for the right. Okay. So if this does not reach, which means if we go from the other side, it won't reach either. Right? Of the two cities, if the two cities are within the range, then no matter what, we can help them reach. Right? If they're within the range. So we can find from one city if its next city is within the range. If it's not within the range, then there's just no way. You have to do it by yourself. If it's within the range, that's good. Then we can see, then they can be handled. And we want to see if the next one is within the range. So if these two are within the range and these two are within the range, then the one in the middle can be maximally benefited. Right? And I do think that, yeah, because each one needs to get. So if we maximally want each one to have, we can go to overlap, and the middle one can get whatever it needs, then that can be taken care of, and then we keep going. Yep, I think this is possible. I think this method is possible. Yeah, it's going to be a binary search. It's going to be a binary search, and we just need to find out if it's possible. And it's not that hard to deal with. It is interesting to find out their indices. So every time we get their index, because if you do the smallest, right, you rank from smaller to high, that will help you know how much we need, right? And then you get that, and if it's all good, then you need to decide their distribution. So now you get their index out, right? You put their index out, you sort them again based on their index, okay? And based on their index, sort again based on their index. And then what? Then you try to see if you can optimally place the k thing in it to make it happen. Yeah. Yeah. Basically, that's how you see. You use up how much. You go to the next one, how many left. You do that. And if you can cover everything, then it's possible. Then you can keep moving and eventually do -1. Okay. I think we have a solution. I'm going to try this tomorrow. All right. I'll see you guys tomorrow. Handle this one. Adios.